Hello, and welcome to my mathematics capstone. Today, we are going to be taking a look at Kronecker's theorem, which is an algebraic structures 2 problem. Now, all of the research done, the writing of the paper, and the making of this presentation was done by myself, Noah Stelmachowicz, and I was advised by Dr. Susan Chera. Jumping straight into the introduction, we are going to find the factors of x squared plus 1. If we took a look in the ring of polynomials with real coefficients, we would find this polynomial to be irreducible. But intuitively, we know that this polynomial is not irreducible because if we looked in the ring of polynomials with complex coefficients, which r of x is a subset of, we can indeed factor this polynomial. That polynomial being, or the factors of that polynomial being x plus I times x minus I. Now, you'd think this example is way too simple for something like this, but this is Kronecker's theorem in practice. And it's one of the things I love about it is that it really is indeed simple to use and put into math problems, but it's actually a really complex proof, which I will outline and kind of show the highlights of here. But before we do that, we have to know what the theorem is, of course. So Kronecker's theorem states that for any field f and any non-constant polynomial f of x in big F of x, there exists a field E that contains both f and a 0 alpha of f of x. Now, I thought that this theorem was worded a little bit difficultly, so I went ahead and paraphrased it, saying that if a non-constant polynomial does not have a factor in our current set, there is a bigger set that contains the original set and has a factor for the polynomial. Again, this is not simple to prove, but creates a simple result. Before we go ahead and look at the outline of the proof, there's just a couple of definitions I wanted to look at just to make the understanding the proof a little bit simpler. So we were going to begin with the ideal of a ring. An ideal is an additive subgroup n of R satisfying those conditions up there. Now you may say, hey, that looks a lot like the conditions that a normal subgroup needs to satisfy as well. And you would be correct. All of these definitions have a very similar definition for groups. It's just that these are definitions for rings, which makes them just a little bit more complex. But if you can go dig out of your brain some stuff from knowing groups, it'll make these definitions make a lot more sense. Moving on from the ideal of a ring, we have the maximal ideal of a ring. A maximal ideal of a ring is basically an ideal that there is no other ideal that contains it within the ring. So in the definition here, M is our biggest ideal. There's nothing bigger other than the ring itself. Finally, we have the principal ideal of a ring, which is very similar to a cyclic subgroup. So if we have an element that is contained within the ring, the set that generates that element, if it is an ideal, is a principal ideal within the ring itself. I also wanted to say, I forgot to mention, that a maximal ideal of a ring is very similar to a maximal subgroup. Heading on to an example here, I'm going to show all three of these definitions at once, just to make it a little bit clearer. And we are going to show that the set that 5 generates is a maximal principal ideal in the integers. To show that it is maximal, we know that, or not that it's maximal, we first need to show that it's an ideal. And we know it's an ideal since any multiple of 5 added or multiplied by any other multiple of 5 results in another multiple of 5. So it is an ideal. To show that it's maximal, we know that in the integers, there is no other ideal that properly contains 5 in all of its multiples other than the set of the integers itself. To show that it's principal, well, because we are looking at the set that generates 5 and we know 5 is an element of the integers, it is by definition a principal ideal. Moving on, having two more definitions here, a ring homomorphism and the evaluation homomorphism. The ring homomorphism is very similar, again, to a group homomorphism. It's just that instead of just checking for one operation to be operation preserving, we need both operations of the ring to be operation preserving under our map in order for it to be a ring homomorphism. In the case of this problem, we have that both addition and multiplication need to be operation preserving. On from there, we have the evaluation homomorphism, which is basically something that we have been doing since middle school. As you can see over here, I have f of c, which looks a lot like f of x, f of y, f of z, all that kind of stuff. And this is just the formal definition of plugging a number into a function and evaluating the function at that number. And it's denoted with whatever map you're using, or not whatever map you're using, but the map from the additive ring we're looking at to the real numbers as phi subscript c of f. And phi, again, is just the map that I defined it by. It could be any symbol, but phi is the most common one to use. To show an example of the evaluation homomorphism, I wrote up one here where we have a function f of c is equal to 2c for all c in the real numbers. We're looking for phi subscript 3 of f. By definition of the evaluation homomorphism, we have that phi subscript 3 of f is equal to f of 3, plugging it in, 2 times 3 is equal to 6. Now we're going on to the meat and potatoes of this presentation, which is the outline of the proof itself. Beginning our proof, we want to select a field, we're going to call it f, and its ring of polynomials, which I'll call f of x. Within that ring, I'm going to pick an arbitrary polynomial, f of x, and an irreducible factor, and we're going to call that irreducible factor p of x. Then the next few steps are going to help us get to this third bullet point here, which is going to show that the factor ring f of x mod the ideal generated by p of x is in fact a field, which I find to be the most critical part of the proof because it's really easy to then create a ring homomorphism between our original field f and our factor ring f of x mod the ideal generated by p of x. Now, a factor ring is very similar to a factor group where we're taking something and dividing it into a bunch of cosets, the elements into a similar group and calling it a coset, just like a factor group does. So once we create the ring homomorphism, we're going to show that that ring homomorphism is indeed an isomorphism, which means that we can represent elements of f in f of x mod the ideal generated by p of x. From there, now that we can work in f of x mod the ideal generated by p of x, we are going to show that our once irreducible factor, little p of x, indeed is equivalent to 0 once we write it as a polynomial and plug it into the evaluation homomorphism. So as you can see all the way at the bottom here, we have that p of x is equal to 0, which is where we're trying to get. So because that was a mouthful and there's a whole lot of different things we have to prove and stuff, I just wanted to highlight 2 of the theorems. Our first one being probably what I would think to be the most critical theorem. If M is a maximal ideal in a commutative ring with unity R, then R mod M is a field. So what we do first is suppose we have a maximal ideal in R. And then what we're going to do is show that this maximal, or that this factor ring R mod M created by the ring and its maximal ideal is in fact also a non-zero commutative ring with unity, which it's great that we can do that in just 3 steps, because then all we have left after that is showing that every element in R mod M has a multiplicative inverse. And simply to show that first it has, or that R mod M is a non-zero commutative ring with unity, since R is in fact a commutative ring with unity, R mod M is a non-zero commutative ring with unity, and you can find more details on that in my paper. So now that we have that, we are going to show that every element in R mod M has a multiplicative inverse. So we're going to take an element of R mod M, and we're going to call it A plus M, and we're going to suppose that it doesn't have a multiplicative inverse in R mod M. So we're going to prove this by contradiction. So if we take this set here, R mod M times A plus M, and examine it, we will find that it does not contain the unity, which is good because that means it's a proper subgroup of M. In fact, an additive subgroup. Now, we need to show that R mod M times A plus M is an ideal, and I have the proof of the ideal right here. Now that we know that R mod M times A plus M is in fact an ideal, and also that we know it's non-trivial since A is not in M, there has to be more than one element in R mod M times A plus M. However, we know, like I said earlier, that it's proper, it is a proper ideal in R mod M because it does not contain 1 plus M. So we're going to choose the canonical homomorphism, which is basically just mapping the elements of a ring or a set to its cosets. We're going to define Y to be that canonical homomorphism for R and R mod M. Now, if we take a look at the pre-image of R mod M times A plus M, we'll show that it's a proper ideal of R, but it also properly contains M. This is a contradiction since we know that M is maximal in R. So A plus M must have a multiplicative inverse in R mod M, and therefore R mod M is a field. That being, in particular, in our case, since we have the ideal generated by P of X being a maximal ideal in F of X mod the ideal generated by P of X is in fact a field, which is critical. Then I'm going to highlight the final proof in my paper, which is showing that F of X does have a 0 in E. So our theorem here, 2.33, states that if F is a field and F of X is in the ring of polynomials of F, big F of X, there is an extension field, E of F, such that the polynomial F of X has a 0 in E. An extension field is just a bigger field that contains the current field we are working with. So that's what E is, and F, of course, is the field that we are working with. So this theorem we're going to prove in particular here for Kronecker's theorem is we have our P of X being an irreducible factor of the polynomial of F of X. And because we proved that F of X mod the ideal generated by P of X is a field, we're going to have E, our extension field, be that factor ring. Then what we're going to do is take alpha and set it equal to X plus the ideal generated by P of X, and then evaluate in the evaluation homomorphism, which I called psi, at alpha. So if we write P of X as a polynomial, where we have P of X is equal to just the standard way you write a polynomial with the coefficients, and then X getting bigger in degree, and we plug it into the evaluation homomorphism, we get that psi at alpha at P of X is equivalent to this thing, which we can then further simplify because we can choose, because since we have an isomorphism, which we created in an earlier proof, again, the details of that are in my paper, we can take elements of F and find representatives of those elements in f of x mod the ideal generated by p of x. And since x is representing the coset in f of x mod p of x, which is what alpha is, we can conclude that p of alpha is equal to this, and this is just by doing a little bit of rearranging. We have the entire polynomial plus the ideal generated by p of x, which is equal to p of x plus the ideal generated by p of x, which is equal to the ideal generated by p of x, which we know is equal to 0. In f of x mod the ideal generated by p of x. Thus, we have found an element in our extension field such that our once irreducible factor of our polynomial is equal to 0. So therefore, we know that our arbitrary polynomial is equal to 0, which is great. Now that we have proven that, we can see that no matter the polynomial, the coefficients are contained within the field, and we can find a bigger field that contains our original field for our 0 and our polynomial, which is what we were looking for. Now, what's great about it is that it has all kinds of different applications, from finding zeros of polynomials, which is what we had to do in order to prove it at all, to finding the critical points for derivatives, which is useful for finding the break-even points in economics. And we can even take it one step further and apply Kronecker's theorem again. Because for some polynomials, in our case, in my example, it worked out that we only needed to find one extension field. But some polynomials, you might have to find multiple extension fields. Now, once you find the extension field that contains all the zeros for your polynomial that you're looking at, that is called an algebraic closure. And a lot of details of that, again, are in my paper, and you can look at it there. Now, if one polynomial can have an extension field that contains all of its zeros, can another? Well, absolutely, because we can prove algebraic closure arbitrarily, which means it'll work for every polynomial. So what happens if there's a ring of polynomials that contains a 0 for every single polynomial? That would be the fundamental theorem of algebra, which is in fact the complex numbers. And that's what I just think is so cool about Kronecker's theorem, is just how it shows how powerful the complex numbers are, in addition to getting a bunch of different information in finding polynomials and finding break-even points, finding derivatives, critical points, all that kind of stuff. So that kind of concludes my presentation. At the end here, I wanted to give a couple shout outs. Firstly, well, I guess one shout out, that shout out being to Dr. Shara. I have had this capstone in my mind since about January of this year, and she's been working with me for the last 11 months to make what ended up being my final paper and this presentation come to fruition. And I just really wanted to thank Dr. Shara for all the time she spent helping me and all the work that she did, in addition to all the work I did to make this presentation and even make my capstone possible. I had a lot of fun doing it, and I really hope that for the people who are watching this, I hope your capstones are going well or went well. And for those who are taking this in the future, I highly recommend finding something that you're really interested in, because it just makes the entire process easier. I had to put a lot of work into this, and if I didn't like the problem that I was doing, it would have been a pain. But because Dr. Shara was so helpful and insightful, and the fact that I actually enjoyed algebraic structures and what we were doing, it just made the experience overall A+, like I hope this presentation is. That being said, have a wonderful day, and thank you for your time.